Objective today is to understand wave equation and transport equation. Wave, I believe in Newfoundland everyone knows what is a wave. You go easily, you can go very close to the ocean and you can see waves. And you also understand transport because all our goods comes from mainland through somehow ocean. So material is being transported, letter is transported. So very general concept of transport phenomena is understood. So in this course and today we'll try to understand two equations. They are basically the same equation. Wave equation written in this form, which is a linear equation. We can verify by identifying the linear operator and we can test whether it supports the linearity property. This is, in the first lecture I mentioned that this is a standard form of hyperbolic equation. So instead of looking at defining hyperbolic equation, I would go and compare with this wave equation. And if the principal part of a equation matches with the wave equation, then the equation is hyperbolic. I will go that way. And then I have the transport equation. All you can see is that if you forget the squares in the wave equation, then it becomes transport equation. You just choose a correct sign of the coefficient c, or in other words, you can just mathematically not correct, but intuitively take the square root of each term of wave equation, then you get the transport equation. So it seems like they are connected, and that is what is we want to understand. And basically, in fluid mechanics, whenever we talk about something interesting, is the transport equation, and whenever we try to look at something complicated but simplified, we look at the wave equation. So there are other applications that we want to look at it. So I'll start with separation variable for today to see how separation variable goes. And then I will jump into method of characteristic, and basically in my view, separation of variable and method of characteristic is the same thing. Method of characteristic comes to chapter 12, and depending on who teaches, sometimes I do not teach method of characteristic. I think it will be taught in 4170 when I teach 4170. But these days 4170 is not being offered on a regular basis, and this is already we can in 4170 we can look at more in depth of the method of characteristics, and instead of putting the characteristics in the very last week and don't get time, so I'm going to relate them with separation of variable and see if we can have a better idea about these methods. So separation of variable, we will treat this like a heat equation or a linear equation. So let me just put the equation here, and I will the same way use a domain which is from 0 to L, and I will not say this is a rod. I will also not say this is a string, because if you go to middle cube just after the class, you can see the waves and they are not string. So I will not explain in terms of vibrating string, which is what in the book. So I will just say, okay, this is a wave, means it's kind of very much you understand wave these days because of the COVID. First wave, second wave, we don't see what it is, curve up, curve down. So we learned a lot over the last 2 years. So that helps me to explain that. So there will be a wave from 0 to L, and then I will use a boundary condition. So I'll consider this is like the frozen rod. So that is why the vibrating string comes on. So say if you have a string fixed on two ends, and then if you can just look at like that. So if this is an elastic material, you could just pull it and then it will vibrate. Okay, so this is one way of looking at it. And now I have a second derivative in time, so I will need two conditions on time. So these are boundary conditions. BC is not British Columbia. Initial condition IC, not intensive care unit, is IC, initial condition. So we'll use the abbreviation BC and IC consistently. So one point to note here is because instead of memorizing, you see the order of the differential operator indicates the boundary condition. Heat equation, we had two order in space. So we had two boundary condition in space, and we had one order in time, we had one initial condition in time. For wave equation, we have two order in time. So we have two boundary condition or two initial condition. In time case, we call it initial condition in time. So this is something, a good learning piece for later on if you go to solve a model and you see a fourth order differential equation and you walk around how to choose the boundary condition, because heat equation I know two boundary condition and the problem I cannot solve because fourth order should be four boundary condition. Okay. So then we will convert this equation into a system of ODE. So convert into a system of two second order ODE. That's the difference between heat equation and wave equation. Heat equation, we converted a system of a first order ODE, which we did not write down because we can solve it analytically, and then we just wrote for one equation. This time, because both equations are second order, so we cannot solve analytically the time part. So we will have to do little bit of trick here. And instead of e to the power lambda t, we will just write h of t. Okay, so then you can differentiate and substitute back into the PDE. So does not matter heat equation, wave equation, Burger's equation, Navier-Stokes equation. If the equation is separable, you take a separation construction like that and substitute back. So you differentiate twice. If I differentiate twice with respect to time, I will get h second derivative multiplied with x. And if I differentiate twice with space, I will get s second derivative multiplied with h. It is just for simplicity, I did not write s bracket x and h bracket t on the right hand side. On the left hand side, h bracket s bracket x. It is implied. Okay. Yes, c square is because You plug into the equation and then you have the c square. Okay, so then you take c square 1 by h double prime t to the left hand side and 1 by s double prime x on the right hand side. So when you fixed in a multivariable calculus differentiation, differentiate a function of two variable x and y, differentiate with respect to x, keep y fixed. So arbitrary constant comes as a function of y, but you say it is a constant. So everything you kept on the left hand side is a function of t, means you kept x constant. Everything on the right hand side you kept a function of x, means you kept t constant. So in that sense, I can say both sides equal to a constant lambda. And we have already learned from heat equation that this constant somehow affects our solution blow up or decay. So it is e to the power lambda t. How it comes in this case is not clear. But in heat equation, e to the power lambda t, lambda is positive blow up, so we want minus lambda. Lambda is negative. So the same way we want lambda is negative, but to make things clear, it will be better if you write minus lambda and say lambda is positive. And the same thing I did in the lecture for heat equation in one way, and in the assignment I asked you to do it in the different way. In lecture I showed e to the power lambda t, said lambda is negative, but in the assignment I asked, perhaps, did I post this as assignment already? So e to the power minus lambda t and lambda is positive. Some more of this type of problem will be coming in the next assignment. Okay. So then obviously you get now two equations. If you take the right hand side, and then if you take the left hand side, you can also write down a boundary condition. And it is very clear for boundary condition for S is S of 0 equals 0, S of L, S at L equals 0. Okay, so for H, we would get a boundary condition or perhaps initial condition. So initial condition not very clear. And if it is not very clear, then I don't like difficult problems. I'll do the easy things. Okay, it's not very clear, so I will not write it down. You don't know it. But now, the good point is if you look at this part. So from the heat equation, we already know that the solutions will be such. So the eigenfunctions So again, values are the same way. You differentiate Sn, substitute there, compare with the eigenvalue equation, similar to the heat equation. Now for h of t, it is still a second order boundary value problem. Solutions are sine or cos. And what we are arguing so far is solution is sine or cos to choose it from the boundary condition. Which one satisfies the boundary condition? And this one, I'm not very clear about the boundary condition. So I'm not very clear of whether I choose sine or cosine. So I'll say a general form. Obviously, we have learned from Math 20 to 60 ODE class and from the first week and half lecture about heat equation that how we can verify it is a sine or cosine and sine when it is sine n pi x over L and when it is sine n pi x over k and when it is sine n pi x. It is just depending on the length of the domain. So we want is going from the left to right and half of the sine wave. Okay. So that's all. And since a solution is sine, a solution is cos, we use the superposition to get, maybe we can also write this is HNX because it is true for n from 1 to 3.
Want them be sine?
Yes, and not only, there is another mistake. Thank you. So then use the superposition. So maybe I can take n going from 0 to infinity. It is less relevant. You can take n from 1 to infinity in this case. Maybe the book, if you look back and look at the book, you'll see that n from 1 to infinity, and then later on discussed how it is n from. So I think for heat equation, I explained that for sine and cosine. So when it is cosine, we start from n equals 0, because cos 0 is 1. For sine, we start with n equals 1 is because n equals 0, sine 0 is 0, so it is just nothing. Okay. So S part is sine n pi x over L. And instead of C1 and C2 is because it is Hn, so the coefficient also will change. So maybe we can write An cos n pi t over L plus Bn sine n pi t over L. Not a bad idea to indicate this is instead of Cn, you can say Cn yeah, Cn does not work. Maybe I can just, what I do is change these two also here. An doesn't matter. So maybe Bn. Because there would be another coefficient for sine, right? So another coefficient in behind sine, and that goes here, makes it C2A and B. But it doesn't, it is an arbitrary constant, so you can just choose it as you like. And then you use initial condition. Now you x0 and from 0 to infinity and pi x over L an, which is cos 0 is 1, when t is 0, sine 0 is 0. And then the second condition, du dt at x0. So sine will be the same. Now if you differentiate that thing inside the bracket, this quantity with respect to t, then and then evaluate at t equal to 0, this term will vanish. This term will come with some coefficient. We can absorb the coefficient here. So maybe we can just write uppercase Bn. And then it's obviously clear that you don't need n equals 0 to infinity, because sine 0 is 0. You can just go for n equals 1 to infinity. And even here, you see, if we start with n equals 0, sine 0 is 0. So although I have cos here, first term vanishes. So this one I can, let's say, remind you. So it could also be the n equals 1. The same thing. Okay. And then
Sn also have a coefficient since it is a solution, or it's like the coefficient just like merge into
in which line?
for s of x. The yeah, Sn.
Here, there's an eigenfunction. Yeah, so we don't write down the coefficient there. So you could put a coefficient, but it is not necessary, because when we use the superposition, we need the coefficient here. And a heat equation, we use the coefficient. Now we merge the coefficient inside. Okay, so basically this equals f of x, and this equals g of x. Now use orthogonality. And you can see this time the solution will be coming here, but now the solutions are not kind of exponential decay or growing. The sines and cosines. So because this part is sines and cosines. So the first wave, second wave is like that. So the wave. So the solution as t increases will grow and then decay and then grow and then decay. And around the world, everyone now knows that without taking 4160, the wave. COVID taught us what is a wave, first wave, second wave. Okay. Any question?
What you were just saying, it's not exponential growth that they take, it's periodic.
Yeah, because the coefficient of sine x, which is ht, is kind of sines and cosines, and maximum and minimum will be plus 1 or minus 1 and the coefficient, right?
Yeah.
So it never will never blow up.
Yeah, it's just these range of values.
Yeah.
This goes up and down.
Yeah, up and down. Yeah, up and down. That is the ocean wave. So that's the difference. Is a little difference. We had first derivative in time. We just made a second derivative in time. With a slight change, the solution is changed. Okay. So it's a little different way of teaching. Instead of lecturing on few weeks about separation of variable, giving you plenty of complicated examples, you see that the big professor, he can solve very complicated problem. We do not understand it. I don't want to prove that I know a lot. Okay. So let's see if we can see what is a method of characteristic. First, I will do a short calculation. I already mentioned that earlier. So I'll rewrite the wave equation, but this time I will take everything to the left hand side. Just for curiosity, I will just write down the operator. So that is the operator for wave equation. And then, okay, it is the same as if I just write the operator. As a quick note, from 20 to 60. Linear differential equation. So we said, okay, d equals d dx. Then we wrote d square is d square dx square. So the same thing, we can do it here. It's like mathematically it is not a multiplication, but it feels like a multiplication. So this operator looks like a square minus b square. A square minus b square, which looks like a plus b times a minus b. So we will use that concept. I will write, okay, so d dt plus c d dx d dt minus c d dx. Outside u. So in the next line, I can go to push it inside. So I can just do it now. So the operator feels like an operator, one operator square minus second operator. It feels like a square minus b square. So high school math, a plus b times a minus b. A plus b times a minus b. How about you think this like w? So then I can push it back to the left part. Sorry, PDE. So then this is a first order PDE. Can I repeat the calculation by switching the order? Just plus sign. So you take the plus sign here and minus sign there. Then this sign will be a minus sign. So let's say switching the order and repeat. So this time let B equals du dt plus C du dx, because the inside part or part on the right side next to the equal sign will be the plus, and this part I denoted by W, this time I will denote by V. So then I will say, okay, dB dt minus C dB dx equals 0. Second, first order PDE. So, final conclusion, second order equation, wave equation, is equivalent to a system of first order PDE. And the difference between those two equations are plus or minus sign of C. So that means we can now think of a different way of solving heat equation. We can just think of solving one of the first order PDE and then combine that to get the solution of second order wave equation. So that's it. So we can separate the variable, is the method of separation of variable, find a series solution, or we can split the PDE into two first order PDE, solve one of them, and then just switch C. Does it feel like machine learning? Because these people talk a lot about machine learning, and we mathematicians, math students are fall behind. So you learn something and then you make a prediction. we taught the world everything. This is mathematics. And the way I will solve this first order PDE is called method of characteristics. Okay. So these two equations are also called transport equation. So now I look at two properties. So just as a reminder, if you have taken other courses from me, you might have heard that do not memorize mathematics. Do not memorize formulas. So mathematics to me is not a plug and play. Memorize formula, plug numbers, get a solution. So I could give you a formula for method of characteristics. Okay, memorize this formula. This is the method. You memorize this formula and then solve. You can do that until the final exam. And after the final exam, because I also forgot. The way I'm discussing is, it is still not guaranteed that you will keep it. But then by knowing those properties, you may use this skill in other parts. You can think of, okay, so I forgot what is the method of characteristics, but I did something like that. Can I try that? So if we can learn the skill, so what are the two properties? Let's consider the first equation. And we see C is positive. So the first equation was dw dt plus c dw dx. Second equation dv dt minus c dv dx. So v and w does not matter. So we can say du dt plus c du dx, c positive is the first equation. We can write du dt plus c du dx equals 0 with c negative. You get the second equation. So that's the advantage here. So if you have not forgotten vector calculus, you know what is a gradient. So look for gradient here. So a gradient operator would be, in my notation, is derivative with respect to one variable and derivative with respect to other variable. If you memorized gradient operator is d dx, d dy, d dz, then you don't see gradient. The gradient operator is an operator, is a collection of first order differential operator, one comma other, second comma other, third comma other, not necessarily three. There could be an infinite number of or finitely many number of differential operator in a high dimensional system. So that's my gradient operator. So then I can say, okay, gradient of u is du dt comma du dx. Now I'm going to define a vector. Well, you can define many vectors, but let's say you can define a vector that fits to this equation. So which vector I could choose? So I'm going to denote it by d, and I'm going to say 1 and c, the coefficient of each term of the PDE. So the coefficient of the first term is 1. Coefficient of the second term is c. I take those coefficients and denote a vector. Now take a dot product. Can you interpret the meaning from vector calculus? What is the left hand side in vector calculus? Directional derivative. Directional derivative of u in the direction of d, i.e. vanishes. Well, this has to be unit vector, but if it is 0, then it does not matter which is the unit vector or any vector. So directional derivative of u in the direction of d vanishes. So when derivative vanishes, what do we think? What do we say about a function? If the derivative of a function vanishes, what does it mean?
There's no
The function is a constant.
negative.
Yeah, the function is a constant. It's a constant function, right? Derivative of a constant, 0. The function is a constant. So directional derivative vanishes. This is something in a lecture or half we do in x direction. Is x direction. Dd y direction in y direction. Dd z directional derivative in z direction. Those partial derivatives are directional derivatives. How about dd a vector? So this is the formula, or this is the rule. It 0 means solution is constant in the direction d. It means